Hello,
Hey,
how are you doing?
good. How about you?
I'm doing good. I'm doing good.
So, what's been going on this week?
Um, we've been focusing on making Triton-VM and Triton-VM recursion specifically faster. So that there's two questions here. One is the prover speed, and the other is the size of the recursion program.
Let's break that down for people that are maybe listening for the first time. So, what is the Triton VM and what is recursion and why is it important?
Every blockchain has a virtual machine of some sort. Well, actually, maybe Monero is a special case here. But even Bitcoin has a virtual machine of some sort, except in the case of Bitcoin, it's a very constrained by design virtual machine. And the reason why it's constrained is so that you cannot launch a denial of service attack on the network by sending a small transaction that causes a huge workload on the part of participants in the network. The thing is with Neptune that this virtual machine comes with a prover and a verifier. The reason why you have a virtual machine is so that all the participants agree on some state update. And in the case of Neptune, basically the state update is presented as in previous state, new state, along with a proof. And this proof is designed to be very efficiently verifiable. It takes 20 milliseconds to verify this proof. But the problem is you have to produce it. And in order to produce this proof, you run the virtual machine, you collect a trace, which is the state of the virtual machine at every point in time, and you do some fancy moon maths operations on this trace to turn it into a proof. And proving is
So,
is
sorry,
that
what is
those fancy moon maths operations.
what is the
Right.
trace? I've not heard that keyword before. Could you talk more about that?
The trace of an execution is the list of states of the virtual machine at every point in time.
So, is that basically the blockchain history until the Genesis block?
No, and it doesn't necessarily refer to blockchains. It rather refers to automata or finite state machines, um, or even a register machine, right? If you define, you could compute a trace of a Intel 86 CPU. In which case, what you would do is you would track the value of every register in the CPU at every clock cycle. And in the case of Triton VM, we have a virtual CPU, but it still has registers. And so we track the value of every register across every clock cycle.
But so someone that's generating a proof, they start with no history, don't they?
Someone who's generating a proof starts with no history, correct?
Okay, so why?
And so, in order to generate a proof that pertains to something that's happening on the blockchain, the program whose correct computation is being proved needs to take a certain input that relates to the blockchain. And this input is typically the hash of a transaction or the hash of a block.
And how does that relate to the trace?
Well, because there are instructions in x86 architecture and in Triton VM architecture that take an input. Well, I'm not sure that instruction lives in x86 actually, but certainly Triton VM has an instruction that takes an input from the input buffer. and it puts that input onto the stack, which is in effect a register in the CPU. And so if you run a computer program on Triton VM whose input is the hash of a block, and you execute this instruction, then that hash appears on top of the stack, meaning it lives in your registers. And then your trace will actually show the hash of the block.
The hash on the block
Of the block.
of the block. Sorry, which block?
About which you are proving some computation.
So the block does refer to the blockchain.
That block just that I mentioned just now, yes.
Okay.
If you like, we can find an example that does not have to do with blockchains, but still has to do with traces.
No, I think that's okay. So you were saying you were working on performance improvement.
Yeah. So the improving the performance comes in two parts. On the one hand, we want to make the prover faster. Prover basically consists of this selection of moon maths techniques that allow us to turn a trace into a proof. And on the other hand, we want to shrink the size of the recursion circuit. And actually, I'm saying circuit, but it's not a circuit, it's a program in our case. Um, and
And just briefly,
we think
again, why is recursion something that you're seeking to achieve?
recursion underscores, enables two key features that Neptune relies on. Firstly, it allows you to replace signatures or proofs of transactions with new proofs of transactions. And so you could aggregate transactions into one big transaction and throw out all the signatures and proofs on the original transactions and replace them with one proof of correctness of the entire batch. That benefits transaction throughput. It also benefits privacy because the lines separating which inputs and which outputs came from which node on the network, they are fuzzy because in order to observe those lines, you have to be online. That information is not recorded on the blockchain.
And so
And
the
the
the,
second
the,
feature,
the first example with the multiple something that has multiple signatures can be generated by something that has one signature. Is that because the multiple signatures can be derived from going through recursion?
no, the multiple signatures come from different people who sign off on different transactions.
So how does having recursion allow you to not have to deal with that?
Not have to deal with what?
With having, because you're saying you're going from a situation where you have multiple signatures to just one signature.
Multiple signatures to one proof.
One proof.
Uh,
Okay.
the signature is a proof of agreement, but it's not a more general proof. It's the least possible general proof. And recursion allows you to take a proof and verify it and produce a proof of that correct verification. In which case, you could throw out the original witness data, which could be a signature or it could be another proof. And so if you have a whole bunch of transactions, whether they are signed or whether they come with proofs, recursion allows you to verify those signatures and verify those proofs and produce a proof of correct verification of that entire verification step. Excuse me, produce a proof of correct verification of that entire step.
But you it's not a requirement to have recursion.
If you're just replacing signatures with proofs, then it's not a requirement. But if you're also replacing proofs with proofs, then it's a requirement. And the reason why you might want to do that is to merge two transactions of which both come with supporting proofs.
Could you make this more concrete, because it's such a central theme? Could you is there an example that may serve here?
All right. James buys a coffee, and Alex gets a gym subscription. These are two transactions that don't have anything to do with each other, but they both land on the blockchain because they happen to be blockchain enthusiasts. Um, Now, they originally come with signatures because both Alex and James sign off on those transactions. Um, but since we care about transaction throughput, and since there is a finite amount of space in every block, we would prefer not to have to store those signatures on the blockchain. So, how do we know that those transactions are valid and that the proper owners signed off on those expenditures if we get rid of the signatures? The answer is we verify those signatures using Triton-VM, and we produce a proof of correct execution of this verification. And then we replace those signatures on the two transactions with one proof on the merger of those two transactions. And so the proof allows us to forget the original um, witness data. And witness data could be signature or proof
And
or
the
something else
and the
still.
recursion part is because it becomes a proof of a proof.
Yes.
Okay, kind of more clear now. Still, um, yeah, like I said, kind of more clear. Okay, so
Maybe the second example is of how recursion is needed by Neptune will clarify things more. In the second example, we actually have recursive block validation. And so every block in Neptune comes with a proof of correctness of the previous block. That previous block itself came with a proof of correctness of its predecessor. So that's recursion right there because the proof itself pertains to another proof. It asserts the validity of another proof.
but how is that different from because in Bitcoin doesn't each block contain a hash of the previous block?
It does, but it doesn't. It doesn't prove its correctness.
Maybe talk a bit more about that, because doesn't because the hash, the fact that the hash is correct tells you that the previous block is correctly represented, and because it also contains a hash of the block before that. No, what's my mistake?
There is recursive hashing in Bitcoin, if you will. I am not sure anyone has used that word. Yes, every block contains the hash of its predecessor. That's absolutely correct. But that hash does not necessarily pertain to a valid block. And so I could produce a block that points to an invalid block. And if I have the requisite resources, I could even make sure that my block has a smaller than target difficulty hash, in which case, if you were to run a Bitcoin node that does not verify blocks, you would be fooled into thinking that my block is the current tip.
Interesting. Okay, so the hash verifies it doesn't verify that that it was computed, that it's valid, or that it was computed correctly.
Correct.
Okay. Okay, with you again. Where were we? Talking about performance improvement.
Recursion, and so since recursion is such a important thing in the architecture of Neptune, we want it to be as fast as possible. Unfortunately, it looks like we're not doing something that's infeasible, but we're doing something that's challenging what consumer grade hardware can do.
Okay, can we make that more concrete? Well, what are we talking?
Well, 2 weeks ago or something, producing a recursive proof using Triton-VM took 1,500 seconds on a machine with 64 CPUs and 800 gigabytes of RAM. Fortunately, we've been able to shrink those numbers to only 200 seconds on a machine still with 64 CPUs, but only 200
What
gigabytes of
kind of
RAM.
machine is this?
I don't know the specifics. I think the CPU is a Threadripper, which I think makes it an AMD machine.
But this is
Uh,
some high end machine. Something. It's not your laptop.
it's a high end machine, and you'll find it in server farms. I guess you could get a consumer version of it, but why would you do that?
Okay,
Um,
but this is we're talking about generating a proof using recursion. So this is at the core of what Neptune is supposed to do. So this could be a transaction, one transaction that you're generating a proof for. No.
it could be a transaction, but if the we have a backup solution here. If the goal is just to make a transaction, then you produce a non-recursive proof of validity of that transaction and of the fact that you're signing off on this transaction. And this non-recursive proof can be proven with orders of magnitude less resources,
Oh,
thankfully.
but isn't that a bit counterintuitive? Because isn't recursion isn't the whole point the performance improvement?
Yes, but there's a limit to which our performance improvements can reduce the cost of recursion, and we're afraid that that limit is we're not afraid that it's infeasible on consumer grade hardware. We're afraid that it's too much of an annoyance to use.
Okay, but before we go into there, how is it possible that you have this other way, the non-recursive way, that's orders of magnitude faster? How's that possible?
Well, because if you're just proving the correctness of a transaction, you're not proving the correctness of another proof, and just the size of that proof alone is reading it is a large part of that cost, and so uh, a large part of this computation disappears if you're not proving the correctness of another proof.
And wouldn't initially most of the activity just be transactions on Neptune? So could they all go? Could they all be proven with this non-recursive method?
Yes, but if you're a miner, then you're only allowed to include one transaction per block. Because as a miner, you can be expected to lift the heavy task of recursive verification. And if you can do that, then you might as well merge transactions by replacing their original proofs with new ones, with one new one. So miners merge transactions using recursion, and therefore, since we want to make mining as widely accessible on consumer grade hardware as possible, we also kind of need to reduce the cost of recursion uh, with an eye to miners.
Okay, and by cost you mean time and just CPU cycles
Time, CPU cycles, and RAM.
and RAM. Okay, and so to
On that note, actually, there's an interesting development that took place, still taking place, where we have a time memory trade-off, right? You pay in time uh, in exchange for having to use less RAM.
okay, we can get to that later. I want to talk a bit more about this 200 seconds. Was that a surprising figure?
Uh, no, we're not the only team to have recursion, and we've heard numbers that are both larger and smaller than 200 um,
And
as their recursion threshold.
and you've only just arrived at recursion, right? Only a couple of weeks old.
Only a couple of weeks ago, yeah.
Okay, and so where are we in the journey? Is it like you've picked the low hanging fruit, or you feel like there's a lot more to be done?
In terms of optimizing the program with the existing instruction set, I think we've picked maybe not all fruits in the tree, but certainly the low and medium hanging fruits. There's not much left to squeeze out of the program itself. Uh,
And am I right?
there are things. Go ahead.
Am I right in sensing a little bit of like not fully satisfied with that? Is that what you're feeling, or how you guys feeling?
Not well, maybe not dissatisfaction, not so much. Just a surprise that the optimized program is still more than a million cycles, more than a million, yeah, clock cycles. That's the surprising part, I'd say, um, because I'd heard smaller numbers from other teams that are also using Starks, recursive Starks.
And is it comparable? Like, is if you were to look under the hood, what they're doing, is it like, oh yeah, that's essentially the same thing, or is it just you know not comparable?
The technology, what is it? That's a very vague term. The Stark machinery is comparable, yes. What's not comparable is the instruction set. And the difference between MIPS and RISC-V doesn't do justice to the difference between our instruction sets. It's a lot starker, pun intended. Um, so I'd say the biggest difference is the instruction set. But in addition to that, there's a feature that makes operating systems out of some Stark engines and programs out of other Stark engines. Because an operating system runs one program, interrupts it, runs another program, interrupts it, goes back to the first, and so on. An operating system is sort of the manager where to spend your CPU time. Um, Whereas a program, it just runs, it has no clue that it's being interrupted. It just runs until it ends. And so, are their numbers comparable to ours? The instruction set and the architecture is one reason why it's not comparable, and another reason why it's not comparable is if they use a different security level. We use 160 bits of security, and other teams generally use less. In fact, I think we target the largest security level.
Interesting. And that's because of it's quantum resistant.
It does not have to do with that, actually.
Okay.
As far as I know, the other Stark projects also get quantum resistant Starks out of it. Um, their security level is just lower because in order to defend against today's attacks, you really don't need much more than 100 bits of security. Um, the motivating argument for our choice for 160 bits of security is that Neptune ought to be secure against Kardashev 2 civilizations, which are civilizations that harvest all the energy available to them within their solar system. And based off of a back of the envelope calculation, they still won't be able to break a hash function with 160 bits of security.
And have you tried reducing that just to see what it does to the performance, or is that too big of an ask?
It's a bit difficult to shrink the hash function. It's easy to shrink the number of queries, which is one particular feature that impacts security. And I don't think we've tried that. No, it's something that we could easily try and see where we compare if we reduce this one parameter. Yeah.
And how? What's next? You've reached 200. Is that enough to move on, or is it like time for a new approach?
Time for a new approach. So we have a few medium hanging fruits on the side of the moon mats, and I'm working right now on new instructions. And so we have a profile of the verifier um, when it's running in the virtual machine, and we know where it spends how much time, and some of those locations where it spends a lot of time turn out to be really, really surprising. And so, for instance, we discovered that it's spending 37% of the time computing an inner product or computing various inner products. That was not on our radar. Um, and so inner products seem to be a very expensive thing, not because they're expensive in and of themselves, but because we do it a lot. Um, and so we decided to add an instruction called dot step, which essentially runs through one iteration of the loop that computes an inner product. So specifically, it reads two extension field elements from two addresses in memory, computes their product, and adds that product to an accumulator. And it updates the pointers. One instruction. Now, it's not there yet because as you add more instructions, you get more loose ends
But
that
how
that
does
can
that
interfere.
help though? I don't
How
understand.
does that help? Well, because previously we had 8 instructions inside the loop to compute inner products, and so 8 instructions becomes one in order to compute inner products. And since
Mm.
inner products are 37% of our uh, profile running time,
Gotcha.
we can reduce that to 5, roughly.
That's the estimate.
That's the estimate.
Okay, that sounds significant.
Yeah.
Okay, so it sounds like you guys are spending some more time on this to really get it down to what kind of number are we thinking?
Well, I'd like 200 seconds, but on this machine
Right.
where I'm calling you from, or maybe after that I'd still like to reduce it down to 100. But the point is that this machine has, what is it, 12 cores, and it doesn't compare well against the machine that has 64.
Gotcha. And how long would it take now with that machine?
It would never complete because it only has 32 gigabytes of RAM, and
Gotcha.
we still need 200.
Gotcha. So you expect this to still be a theme for the next weeks ahead?
Yes,
Okay.
yes.
And how does the maybe one of the final questions for today's session, but how does this relate to the overall roadmap? Or do you still on schedule, or how does that look?
Well, the schedule is always hazy going forward. We still expect to launch later this year, within a few short months, in fact. But there's still a lot of code on the side of Neptune Core, which is the blockchain client that needs to be written, and that depends on recursion. And so if we have a slow recursion on the side of Triton-VM, then yes, we could write those pieces of missing code, but our feedback cycle would be very slow. Feedback between writing code and testing if it is correct. And so part of the reason why we're focusing
Gotcha.
on Triton-VM right now, to make it faster, to make it run on this computer, is so that we can run through that cycle faster later on.
Makes a lot of sense. Yeah. Okay. And what are some other major chunks that are coming up in the roadmap?
Of Triton-VM or
No,
of Neptune
before
Core
launch, yeah, just in general.
before launch? Right now we have a testnet, but testnet is not feature complete. There is some proving going on, but it's not recursive proving, and so one milestone that we definitely need to get to before launch is testing a feature complete network where you can do these two types of proving, merging transactions and proving the correctness of previous blocks. Um, and in fact, the logic where you tie in this recursive prover with the consensus of Neptune hasn't been written yet. So we'll need to write that soon.
And anything else?
I guess on the side of Triton VM, we still have a couple of big and medium hammers to throw at this problem, both on the side of Moon Maths and on the side of new and improved instructions. And yeah, for the foreseeable time, we have orders of magnitude improvements awaiting ahead of us. And I think we'll only shift focus to Neptune Core after we ran out of potential orders of magnitude improvements.
Okay, cool. I think
All right.
that's a wrap.
Sounds good. Take care. See you next
All
week.
right,
Oh,
see you.
hang on. We're missing next week, right? See you in
See
two
you next
weeks.
week. See you in two
Ciao.
weeks. See ya.